Yeah, so maybe first let me, before I give explanations, thank Vladas and all the organizing committee for this invitation and for their kind invitation and for this beautiful organization. So I announced Markov and Fock, but I must say that I have to admit that I know essentially nothing about these two gentlemen, and not even, I have no picture to show, and I don't even know their first name, I'm afraid. So after preparing the talk, I discovered that an alternative title could be the determinant of the green function. The determinant of the green function. Of course, this morning there was an introduction of the green function for two-dimensional Brownian motion, and since you are a mathematician, for most of you, you might feel a bit uneasy and using determinants of this object, which diverges on the diagonal, etc. So I'm nevertheless going to resist on that title, and therefore I will consider during most of my talk a simple case, much simpler than two-dimensional manifolds, which is the case of a graph. So we'll consider a general graph that is a set of vertices which be finite or countable, and a set of edges. We don't assume it to be planar. We don't assume it to be embedded. It's just a graph. And then, well, nevertheless, sometimes you can indulge into pictures, you see. So vertices, and there will be an additional or a specified vertex I call delta, which will be a symmetry point. Since we are dealing with Markov chain, this can be useful. And what you do is you do the standard thing, namely on edges, you put conductances so CXY, which are indexed by the edges of the graph. And on vertices, you put weights, which are killing rates, which can be 0. So this defines a kind of discrete geometry on the graph, which is well, everything is embedded in a notion of energy. So if you take a function on the vertices, this energy is defined as the sum, 1/2 the sum of Cxy, the variation f of x minus f of y square, plus sum of kappa x f of x square. And this is the analogous of in the continuum of, well, you may have a symbol, aij of x, and then df over dxi, df over dxj, sum, integrate dx plus some potential against f of x squared dx, and integrate on some domain, possibly with directly boundary conditions. So since this has to be a little bit, well, I want to make a smooth transition with the lecture of this morning, which was designed to be elementary. So let me just explain why is this, what's the relation between the two. It's not just analogy. You can go in both directions. One is, of course, when you have a continuous space, you can discretize it by taking triangles or something like that. And when you have a discrete space, you can take continuum limits. So scaling limits. So for example, if you have a bounded domain of R2, what you will do is take this kind of thing, and then the conductances would be essentially all the same, 1 if you take the Laplacian, and you will have killing on the boundary. So it will be killed. That will be the directly boundary conditions. And if you want to add a potential to your Laplacian, then there will be some killing inside. See, so that's. Now, let me stick to this discrete framework. Then I have to introduce the associated Markov chain. So there is Markov chain, Pxy, which is Cxy, the conductance normalized. So the normalization lambda x is the sum of Cxy plus kappa x. So this is the sum on all y connected to x. And actually, you can see that this kappa x can be, in a sense, understood as a kind of conductance between x and delta, but there is no way back. Well, at least not for this Markov chain. You don't allow to come back. Right, so this is a lambda symmetric. So you can view lambda as a measure. There is an L2 space, and you get an operator which is symmetric in L2. Now, the Markov chain we will consider are actually indexed by continuous time. So it means that at each point, you will wait an exponential time. It doesn't change very much, but it will be useful for what we wish to do. So, in fact, what you have is a semigroup, some Markov semigroup, which can be written as the exponential of t times I minus p. This is an exponential of matrices, just the way that the heat kernel can be used, written in functional analysis as the exponential of t over 2, the Laplacian. Yeah. So you consider this semigroup, and then there is a green function. So the green function can be defined, well, in two ways, several ways. So first formula is that it will be 1 over lambda. So let me define it as g of xy. This is a symmetric function in x and y vertices. X and y do not need to be connected. Of course, it goes far away. And so this is the sum of pk, so potential, if you want, xy, divided by lambda y. You can forget a little bit about the lambda if you're not too familiar. You can suppose that they are all 1 if you want. But, and another way is to write it as the integral from 0 to infinity of pt xy dt. Again, I have to divide by lambda y to get something which is symmetric in x and y and not lambda symmetric. And another way is to say that this is also equal to the inverse of this matrix So this is a diagonal matrix with entries lambda. So if lambda is 1, it would be just the identity, minus the matrix of conductancy. So this is the inverse. You see, this is essentially the analogous of the Laplacian. And this formula is the formula that Van Lin wrote, saying that the green function is the inverse of the Laplacian. This is this formula in this elementary discrete framework. You mentioned it's very general, and actually it's very general. It works even in the simplest case. So that's about all for generality, but still I need something which was not mentioned this morning, but I will assume you heard about it, namely the Feynman Cac transformation, which is adding a killing rate to Brownian motion or to any Markov process. So this means that you add to the killing rate some additional chi. For example, if kappa was 0, you just add chi. And then it changes a little bit so that you have the same path for the Markov chain, but they die earlier. And the green function is modified. It becomes g chi. And the way it is modified is very simple. You have g minus g chi. G chi minus g is just minus g multiplication by m chi g chi. So you see, this is essentially the resolvent equation. When chi is constant, this is exactly the resolvent equation. So it's just a little generalization of the resolvent equation. Now, so this was the framework in which we will start to work. And so I will start with spanning trees and Wilson algorithm, because they were mentioned to you by at least by Vincent Beffara. So I will start there. And so it's a procedure, Wilson algorithm, that produces random spanning trees. So maybe let me just say, why can one be interested in spanning trees? I mean, of course, this is not a question which has a unique answer. So I'll just give you my favorite one. When you have a graph, you see, when you have a graph, above it there is something which is called the universal covering, which is a tree above the graph, and which projects on the graph. Just like if you have a Riemann surface, there is the hyperbolic plane above it. If you have a circle, there is a real line above it, etc. Simply connected. So there is a canonical projection from this tree and this graph. And when you have such a situation, you want to, sometimes you need to find a section and to go up. And there are several ways to go up, not only one. And fixing one way to go up means fix a fundamental domain in geometry in general. And in this case, the fundamental domain, they are the spanning trees. So you see, for example, here, you could use this one. And it means that you go up like that. And just, but there are different ones. Like, for example, this, and this. So this will give you a different section. So spanning trees are essential geometric objects. And the way Wilson algorithm proceeds to construct them is loop erasure. So loop erasure, I think it was introduced by Growler. So you just proceed with your random walk, which now, for the need of this picture, becomes a continuous path, but don't worry. And well, progressively, you erase all the loops that form themselves. And you end up with a path which is self-avoiding and necessarily ends up in delta. So you do that, and once you have finished, so first, to do that, you start with a point. So you have to put an order on the points. And this order turns out to be irrelevant. So you start with the first point, do that. Then do the same thing. So this will be x0. Then you do the same thing for the first point, which was not the second point. Well, after all, the next point after all those which have been visited, which are not in the order you chose, of course. And you do the same thing till you get the first pass, etc. So you produce a tree. You produce a tree which spans the space, at least in the finite case, and which is rooted in delta. So in fact, by choosing delta, we fixed an orientation on the tree, which, of course, is arbitrary. And we'll see that the result of spanning trees doesn't depend on the choice. So the law of the spanning tree can be computed. So the probability is that Wilson algorithm, WA, applied to the graph VE, gives you a certain tree, certain spanning tree tau, can be computed as the product on all edges of tau of their conductances and the product on all x connected to delta in tau of their killing rates times the determinant of G, which now in this setting is a matrix. So why? So you see here, you see that this kappa x actually plays exactly the same role as the conductances from the edges which connect x and delta. And why do you see this determinant? So again, since we are in continuity with this morning, I will want to give a little hint of the proof why this determinant appears.
Is it kappa x only one vertex that is connected to delta?
All x connected to delta. So,
but it is a tree.
yeah, but the tree is rooted, you see. So at some point you jump to delta when you die. Right, so let's see how it proceeds. So we just look at the first step of the algorithm. What happens? So let's suppose that we start at x0, and we first go, the first step of the tree will be y. So when does this occur? So this will be the probability. So I assume that in the tree, in tau, you have this. So I want to compute this quantity. And then I will say that this is the sum in all k of probabilities for the random walk, well, the Markov chain starting at x0, that xk is equal to x0, and then xk plus 1 is equal to y. And then I assume that k is the last time I visit x0. So then I will get, by Markov properties, I will get the probability starting at y that the Wilson algorithm, sorry, it's not Markov property, that Wilson algorithm applied to the graph without x0 gives you the tree without, tree tau without, I'm a bit rough here, without x0, say. So you just, and you sum on all k because, well, this can happen at any, possibly at any time. So when you compute this, you will get a sum of pk. This is a k-spore of p x0, x0, p x0, y, and then this quantity, same quantity as before. And here what you see is this sum in pk, it's I minus p minus 1. So essentially the generator in x0, x0, then p x0, y times the same thing. And now you can reformulate this. You see, well, I have to go fast. So let's say what you see here is the inverse of a matrix, right? So how do you compute the inverse of a matrix? By Cramer's rule. So when you put Cramer's rule, you get determinants. And what you will get here, actually, this quantity by Cramer's plus the definition. This will be the determinant of G, green function, divided by the determinant of the green function of the process outside x0. So you kill the process in x0. x0 is absorbed by the symmetry, in a sense. You get a different green function. So this corresponds to the cofactor in Cramer's rule, times cx0y times the same quantity which was defined here. And so you just see that the det of G is there from the beginning. And then after, of course, it goes with another term, another det of G, which you don't want. What happens is that they all cancel out step by step, and the only determinant which is left is the determinant of the green function. So that's how the proof goes. Now, I thought I will never finish that blackboard, but eventually. Right. So. Yeah. So in particular, what you get is if you take the sum, since a probability has to be a probability, you see when you take the sum in all tau of product of conductances, product of killings with x goes to that on all x's connected to the symmetry, what you will get is the determinant, 1 over det of G. And this is a generalization of Cayley's theorem, which counts the number of spanning trees. If you take all conductances equal to 1, you get Cayley's theorem. You see, by the way, that on this formula that this det of G does not depend, cannot depend, since these are actually conductances between x and delta, cannot depend on the choice of delta. So this green function, which depends on the choice of delta, its determinant does not. Why is that? Well, the reason is that actually there is a green function. If you don't put killing in delta, then you get a recurrent process. Recurrent process, a priori, the green function does not exist in the sense that this theory diverges. But if you restrict it to functions with zero mean, then you have chances that it exists. And it actually is the determinant of this operator, which is the value of det of G. But, well. Now, I will stop proving things. And I will say that more generally, well, proving was maybe a bit too much, but trying to prove things. But I would say that more generally, if you do the same calculation, but a little bit more refined, there is one thing you can do in graphs. You see, usually when you work with diffusion processes, you fix a generator. Just have one. Sometimes you move the drift by Gesanoff, or you add the killing, but it's difficult to change the symbol. So in this situation, of course, you can vary the conductances quite easily. So the expectation under this spanning tree law, so with respect to the conductance I defined, of course, of the product of C prime xy over Cxy, product, of course, on xy in tau, product on x connected to delta in tau of kappa prime x over kappa x. this will be the determinant of G, the grain function, divided by the determinant of G prime. G prime being the grain function associated with this other set of conductances and killing rates. So I want to keep this formula. So stop me if I try to erase it. Right. So now we have to talk about the loops, because in this Wilson algorithm we forgot some loops which were erased, and the idea now is to collect these loops and see what they look like. So there is one thing, one calculation which is easy to do, again along the same lines. So I will denote LW, W for Wilson, or LWA, the set of erased loops. When I have a loop L and X a vertex, I can define L at X, local time of L at X, which is just the time spent by L in X. Well, I divide by this lambda X, which is always there. And so one thing I should stress here is that the Markov chain had holding times. And what we decide to do when we perform loop erasure, which is usually performed in the context of discrete Markov chain, is that the holding times stay on the loops. So you see, for example, each time you pass with a point, there will be a trivial loop, possibly. If you don't come back to that point, there will be a one-point loop with holding time there. So the holding times are on the loops. The tree has no hold there. You don't spend any time. It's just a self-avoiding discrete path. So all holding times are collected in the loops. So I can define this. And then I will denote by L WA hat X the sum of all L hat X for L loops in this set. It's a total time spent by all the loops I erased in points. That's actually the total time spent by the Markov chains I created in these points. Now, the same, essentially the similar calculation, if you keep track of what happens when you did the calculation here, there were p to the k. You see, these were loops, actually. So you have to look at what happens here when you consider holding times and use Feynman Cac. So what you gather from that is you can actually compute the Laplace transform of this field. So you can compute the expectation of E minus sum in all x of chi x L hat WA x, and see that this will be determinant of G chi divided by determinant of G. Now, you know that these determinants don't make sense very much once you go in the continuum. So the point is, I think it was already mentioned by Julien, that quotient of determinants tend to be more often defined than determinants. So here, I remember, well, there is this formula here, the resolvent equation. So if you use it, you see that you can actually simplify this quotient of determinant and get that this is a determinant of identity plus multiplication by chi g minus 1, which, but for the sake of symmetry, we can as well write as determinant of I identity plus m multiplication by square root of chi g multiplication by square root of chi. So then we have a symmetric operator. And if you know a little bit of functional analysis, or even, you see, determinant of 1 plus something, the determinant is a product of the eigenvalues. So product of 1s is fine. And then you have to need some convergence. So even if there is an infinity of eigenvalues, this can exist. And for example, for one-dimensional Brownian motion, this will exist. This makes complete sense. So this set of loops, what we know up to now is this result here. So I want to catch it from another side. So this is a way to catch it. There is another way to catch it. This is the way Lawler and Werner introduced when they introduced the loop soup for two-dimensional Brownian motion. So in fact, this construction is completely general again. So what you do is that you introduce a notion of Markov loop. So I'm still in Markov, you see, not making too much progress. Markov loops. So I have to, so you start with a bridge measure, PTXY. That's a bridge, but it's not normalized. So the mass, you just write a bridge like Markov chain, and the mass will be PTXY over lambda y, so that it's symmetric in x and y. And then you introduce the loop measure by taking bridges from x to x and integrating in time in a certain way. So you just take the sum in all x of lambda x, integrate from 0 to infinity in time of 1 over t pt xx. So this is a measure on loops, which is sigma finite. It's not finite because of the 1 over t here, at least. And this object is actually very nice. So let's see what's a few properties of this object. First, in this setting, a loop is defined by a certain number of points, and then holding times. So you have points, and then certain holding time. So there is a so there are trivial loops with only one point and a certain holding time. So for example, if you look at the measure of such a loop, so mu of p equal 1, psi equal x, and tau belongs to dt, this will be e minus t over t dt. So that, you see, here you have divergence. So the mass of these one-point loops is infinite. But for example, if you look at the measure of a certain, you want to have psi1 equal x1, etc., psi p equal xk, and p equal k. This will just be, so p is a number of points. This will just be p x1 x2, etc., p, xk, x1. So you just come back. And you need to put a 1 over k in front. Because you choose a starting point. If you didn't, you have to choose a starting point among k possible starting points. So, for example, the mu the measure of loops with k points appears to be the trace of p to the k. From that, you get that the measure of loops with more than 1 point is minus the logarithm of determinant of I minus p. This is just by expansion of the logarithm and the determinant. That's sum of 1 over k trace of p to the k. And this actually is the determinant of, well, it's a logarithm, again, of the determinant of the green function g divided by the product of lambda x. So, in a similar way, using again Feynman Cac, you can compute mu applied to E minus sum in x of kx L hat x minus 1 and find that this is the logarithm of determinant of g chi divided by determinant of g. That's similar calculation. Now, once you have that, there is one step, which is to go from one sigma finite measure on loops to a probability on configuration of loops. So you take a Poisson process with intensity mu. Just take a Poisson process with the same intensity. So you introduce L to be the Poisson process of loops with intensity mu. And then this is essentially a set of loops like here. And you find out that this actually is true also for this new set of loops. So you find exactly the same distribution for occupation field, for local times, total local times. So this suggests that these two sets of loops are not so different. And actually, you can recover the set of loops you get from Wilson, well, from the set of loops you get by Wilson algorithm, you can, by adding a few random variables, which cut the loops, because you see, by Wilson algorithm, the set of loops a priori seems to depend on the ordering of the points. First, you collect one big loop which visits the first point. So you have to cut a little bit this loop according to some Poisson-Dirichlet distribution and find exactly an identity in law. So you get, of course, this structure using the loop measure and the Poisson process is much more transparent. And now you feel that you understand what is this set of loops. Now, the last thing is that this expression, so now we forget a little Wilson algorithm, and we'll come back to it, though, but focus on this formula. So this formula gives us the Laplace transform of a field, the occupation field of the loop set, as a quotient of determinants. Well, if you know a little bit Gaussian variables, it's easy to recognize that this expression is the same as so you can write it, maybe I should, well, no, I don't think I have time. So you can write it as the expectation of E minus 1/2 sum in x of phi x, phi bar x, where phi is a Gaussian, a complex Gaussian vector. Phi, well, this is a complex free field. Namely, here in this situation, the Gaussian vector, complex, centered, with covariance given by the green function. Just when you write formally, this calculation is extremely easy. You just it's a formula which gives you the absolute continuity relation between two Gaussian measures. You have a change of normalization, which is given by this. The determinant appears in the normalization of the Gaussian measure. That's all to explain this. So you see, here again you have, with Kx, sorry. So here again you have a Laplace transform. Exactly the same structure. So this tells you that this loop, this occupation field of the loop ensemble, L hat x, has the same distribution if you consider it as a field. So for jointly for all x in V, this has the same distribution as the square of the complex free field, 1/2. That's the same law. Again, this will remain true in dimension 1 for buoyant motion, for which the complex free field is essentially the free field is essentially the Ornstein-Uhlenbeck process. And so, we'll see in dimension 2 there will be more problems, so I don't think I will get to that. So, well, let's say that a renormalization is needed, and you have to perform Wick renormalization on that side, and some renormalization of the type you do for Levy processes in this one, so compensated sums. But this will remain true, essentially, when provided proper definitions are given. Now, I have to come to Fock. So this Gaussian field can be viewed in many ways. And it has an important structure which is called Fock space structure. So the Fock space structure appears as follows, can appear as follows. So define this operator on functional on the field. Square root of 2 sum in y of gxy d over d phi x. Let me call this is a differential operator. Let me call it ax. Then you can define similarly bx, same thing but with d over d phi bar. Well, so variation of the field. This is what you do sometimes when you do Maillard calculus. See, you differentiate along the path. Also when you do dynamical percolation, by the way. So you can look at the adjoint. So for example, A star x is going to be phi x over square root of 2 minus square root of 2 sum in y of gxy d over d phi bar x. So there is a remarkable structure that appears, which is that operators ax and a star verify certain commuting relation. This is a commutator. This means the commutator of AB. This is AB minus BA. So you have this commutating relation, the same with B, and all other commutators vanish. So, moreover, you can check that A1, AX1 is 0, etc. And moreover, you see that phi is just square root of 2 A plus B star, and similar formula for phi bar. So you can actually reconstruct phi and phi bar from this commutation relation. In a sense, once you have exhibited this structure, you can make a revolution and say that the beginning, the end becomes the beginning, and you start with such operators, with such commutation relation, and then you reconstruct the whole thing, the Gauss and all the thing. So there is no need for Gauss measure, no need for nothing. You just start with the gxy and create the whole thing purely algebraically, like you get a group from the relations. So you can do that. I don't have time to explain very much. So that now you see phi is actually an operator. It's just an operator of multiplication by phi. This operator commutes. But everything does not commute. For example, since you have derivatives, things do not commute. So you are in the realm, if you want, of quantum mechanics now. So everything does not commute. But it contains the free field, and this is essentially in that way that free field is used by physicists. So let me write one formula. So if you want to compute an expectation of phi and phi bar, this will just be in the Hilbert space, which is isomorphic actually to the L2 space. You can just write it as one scalar, the function of these operators, which commute, applied to 1. And in particular, you have that 1 exponential of minus 1/2 E prime. So E prime is the energy associated with a different set of conductances as before, of phi bar plus 1/2 of E phi applied to 1. This will be the determinant of G prime divided by the determinant of G. So what I say is more or less all the calculation you do on Gaussian fields, which are related, as we said, we saw, to the occupation field, can be interpreted algebraically, if you want, using this creation and annihilation operator. So the L2 space becomes the Fock space, and this Fock space is a sum of symmetric tensor powers, which are constructed using annihilation within creation operators that goes from one level to another. It's a generalization of the decomposition of the Gauss measure in Hermite polynomials, as a sum of Hermite polynomials. You do it now in full generality for any Hilbert space. Now, my point is that this Fock space is called bosonic Fock space because it is symmetric tensor power and because here you have commutation relations. But it has a partner in life, which is the fermionic Fock space. And this fermionic Fock space, it's the same essentially, except that you don't commute, you anti-commute. See? You anti-commute. So everything which was symmetric becomes skew-symmetric. Commutators become anti-commutators. And so now the situation in matters of time becomes really dramatic, so I have to do things which are a little bit. So you see, you just put commutators, anti-commutators instead of commutators, and well, let's replace the A by C's and the B by D's. Yeah. So yeah, now you will get not phi, but psi. And here I will put, I will put, well, it doesn't matter too much, I think, now, but things like that. And I will have a psi bar. So now I'm with things which don't really make sense in terms of probability, since I'm not anymore on the Gaussian space. I'm not on the same Fock space. But the structure is very close. So psi and psi bar now anti-commute. If you want to find an analog with the calculus, you have to use differential forms instead of functions to find an analog of that. But here I chose to present you the real thing, namely the Fock space structure. Now, why should you care after all of this? See? Why care? Okay, Fock space, so what? Well, the thing is that this fermionic Fock space appears to be related with the spanning tree. In a very similar way, the Gaussian free field is related with the loop. So that you have, in fact, a kind of quadrangle with loops, trees, Bose, and Fermi. So I have to explain how this relation goes, and I'm lacking time. So let me just say that what you can do is the law of the spanning tree was given by this formula, which involved determinants. Now I want to reinterpret this formula in terms of this psi and psi bar. For that, I will recall this formula, which is a formula of Gaussian calculus. It's easy to admit that this formula of Gaussian calculus should have a partner in life also, where you replace phi by psi's. And so this relation between when you replace phi by psi is called supersymmetry. And there is a lot of miraculous cancellation that occurs when you do that. So in fact, here, if you do the same thing, but with psi bar, and now you see, you really have to write it with brackets like that. You cannot write it as an expectation. There is no expectation around. But then what you find is just the same thing, except the prime is here. So just the inverse. And so it's exactly this formula there. Now, is this of any use? Well, yes. If you consider C prime as a variation of C, so you just move C a little bit at certain sites, what you can differentiate, in a sense, this. If you differentiate on one side, do the same differentiation on the other side, what you get is a formula which gives you the probability that the spanning trees contains a certain number of vertices, edges. So, for example, you will get the probability that xi, yi belongs to tau. And you will see that this will be the product of C, xi, yi, so the product of conductances. This could be 1 in certain cases, for example, in the case where all conductances are equal to 1. But then the important term is 1 times the product of 1/2 psi xi minus psi yi psi bar xi xj minus xi minus psi bar yi. Now, this is just a polynomial, and the evaluation of it is not more difficult than the evaluation of the same Gaussian polynomial. So Gaussian polynomials or monomials are evaluated using permanents. These ones are evaluated using determinants. So permanents for Gaussian, determinants for these ones. And what you get in this way is a result which is known, which is the transfer impedance matrix theorem. So you get this as a determinant of k xj, xi, yi, xj, yj, where k is, so k xy uv, this is just g x u plus g y v minus gxu minus, gxv minus gyu. So essentially the green function again. Right, so my time is almost over. And I have to say a few things on how these things go or don't go to the continuum. So as I told you, in dimension 1, many things are true. For spanning trees, you get interesting things. So maybe in dimension 1, for example, what are the loops? You see the loops, they are actually Brownian excursions. If you look at them from the infimum point, you get Brownian excursions, and you get a Poissonian set of Brownian excursions. So what is it? What is the occupation field? So this occupation field, how much time do you Brownian excursion visit a certain level? This is a branching process. This is a continuum branching process. So when you add up all these excursions, you get a branching process with immigration. When you look at the spanning trees, well, you need to have some killing rates. So So you see there will be some points which will be killed and will jump. So the spanning tree will be like intervals, just like that. And these intervals, endpoints can be connected. Sorry, no. There are some points in the intervals which are connected with the Laplacian, with the symmetry. And so you have to find the law of these intervals. And this, again, it involves determinant. So it will be a determinantal process. A law process with law is given by determinant. But here, since it's one-dimensional, it will have an additional property, namely the fact that the spacings are independent. So it will be a renewal process also. And these were actually the first determinantal processes which were constructed was by Mac. You get them in this way. So you get many things of one dimension. In 2 dimensions, renormalization is needed. And what I can say is that it's easy to see that the Vic renormalization corresponds to the compensated sums renormalization for local times. And also to one thing, which is a determinant. So what you have to do, what is instrumental in this matter is the notion of renormalized determinant. So there is a notion of a renormalized determinant, det2 of I plus A, which formally writes as determinant of I plus A, E minus trace of A. And the thing is that this can happen when this can exist when A is Hilbert-Schmidt, even if this does not exist. So you have to use these determinants to give formulas for the Laplace transform of this renormalized occupation field, which formally are obtained by subtracting the green function which diverges. See, there are 2 things which diverge, which is the occupation field and the green function. But the difference does not diverge. And when you compute the Laplace transform, you find a simple exact result in terms of renormalized determinant in that point. So I know I'm going too fast now, but I'm sorry. Well, that's all for today. To interacting fermions? No? But there might be some. You mean you want a higher interaction with higher powers? Or with? Well, you probably. No, we are still at the level of the free field. No, but I'm ready to learn. What? Okay. What is it? I didn't. Vladimir? Oh.